Okay, welcome to class, everybody. Happy Friday. So today we will talk some more about stacks and queues, and we'll actually write at least one algorithm using a stack. So that should give you good practice for project 4, where you're going to write an algorithm using a stack and an algorithm using a queue. I think that those will be good, healthy challenges, so don't wait till the last minute. Get started on those early. I think a lot of you saw the recording from last time was kind of weird, so you can look at it if you want, but hopefully everything should be back to normal now, because I didn't have my iPad set up last time very well, so now everything should be moving more smoothly. So let's just jump right in. So, okay. First thing I want to do is just review stacks and queues. So last time we talked about abstract data types being ways that we can basically specify what data a data structure holds and its methods, and not talk about the implementation. So for example, for a stack, we have the data, we can have stacks of any data type we want, but our methods that we have are push and pop are really the key methods, and we can think of this like a spring-loaded plate dispenser. So whatever is on the top of the stack, that's when we call our pop method to remove what's on the top, we remove what's on the top. And so if we contrast that with a queue, I like to have these pictures in my mind of stacks and queues. So if I think about a stack and maybe I'm just going to add the numbers 1, 2, 3, 4, 5 to my stack. I always think of stacks vertically. So if I add 1, which I would do by calling push, I add it to the bottom. And then if I push again and say I push a 2, I push a 3, I push a 4, I push a 5. And so for a stack, we kind of think of, when we push at the top, and when we then remove, we call pop. We also pop from the top. So if I was to call pop, then I would pop off the 5, and I would remove the 5 and return the 5. Pretty simple. So for a queue, if we thought of the same thing, let's just try to remember what those methods are called. So let's say that I'm adding things to my queue. Does anybody remember what the method to add to a queue is? Kind of a weird one, yeah. Yeah, so push is for a stack. So yes, NQ, yeah. Kind of a weird one, but that's what it is. So when we add to our queue, that is called N. Oh gosh, did I use my queue? Yes. And so let's say I call that 5 times again I call it with 1, 2, 3, 4, 5. But now if I wanted to draw the analogous arrow for the pop for my queue, so here with the pop, I was really trying to indicate that when we pop, we take from the top, right? So we would take off this 5. So can anyone tell me what's the analogous method name for a queue?
DQ.
DQ, yeah. And if I wanted to sort of draw, which one am I going to DQ? Well, what am I going to return when I DQ? Yeah, go for it. You can be the DQ guy. Great. 1. And so if I wanted to sort of draw an analogous picture, I might say that my DQ arrow is down here, right? DQ. This is even harder when you have people watching you. Okay, great. So stacks and queues. Simple but very useful data structures. And okay, what I want to show next is Java's stack implementation. So you're going to write your own 2 stack implementations, and those are, you're going to write those and you need to implement that interface that comes down with Project 4. But if you were out in the working world, or I don't know, you're just writing a Java program for fun, you would not want to implement your own stack, even though you could. It'd be pretty fast, but you don't need to. You could just use the Java built-in stack. And so I'm going to, there's a link to that on the Wednesday's lecture page. You could also find it just by Googling Java API. Maybe we could even do that. If I Google Java API, which is probably really small for you, if I Google Java API, and then really the first thing here, and since this is Java 7, I usually just go to the URL and change it to, I think we're using 17. There may be a slicker way to do this, but that's how I always do it. And then you could just search for stack, and we see that there is a java.util.stack. And this is generic, just like ours. And we can look at this and see, when it's this big, it's kind of hard to see see the methods and stuff. But yeah, here we've got our pop, returns element, returns something of data type E. We've got push, etc. So yeah, you can't use this in Project 4, but you're welcome to check it out. And we're actually going to use it in class shortly. Are there any questions about this? Great. So let's move on to a implementation of, or an application of stacks. So last time we saw this slide, but I would say even simpler than all of these. Let's say that I just want to reverse an array. So say I have an array, it's called data, and it happens to be holding 1, 2, 3, 4, 5, but it could have been an array of any type, of any length. But here is data, and I want to reverse it. So I want my 5 to be held in slot 0 instead of my last slot, etc. Can anybody think of, first off, any way that I could do this, sort of? Doesn't have to use a stack, but if it does use a stack, that's cool. Yeah.
Instead of using you can still use 0, but instead of just using 0, you would do the length minus 1 minus 0, or where you are.
Oh, yeah, since they're ints. Yeah, so yeah, that's a really good idea. So because I happen to have, okay, so we got some ideas. So because my data type happens to be an int here, I can leverage that and say, well, okay, these happen to be, this happens to be in order, but just to make sure I understand, your idea wouldn't work if these happen to be in order, but if I, say my array had been 10, 1, minus 2, 4, 5.
I see. I'm sorry.
No, I like your idea, yeah.
I was thinking that we were reversing it from the start, so when we put them into the array.
Oh, yeah.
But
No. I like it. But yeah, so if I had this array of ints, then I would, when I reverse it, it would go 5, 4, minus 2, 1, 10. But this, yeah, not all inputs, we'll say. Okay. Any other thoughts about how, so I start, data looks like this, and in the end I want data looks like this at the start. And this is what I want data to look like at the end. Yeah.
So thinking about it, when we're using stacks, you could pop them all or push them all into a stack, and then pop them all back out in like a different order using like a different type of loop. But wouldn't that be really inefficient?
Well, what are you thinking about it that would be inefficient?
So if you grab each element and put it into a stack, that'd be n.
Mm-hmm.
And you have to take them all out again, so then you work with n squared.
Well, yeah, what you're thinking, yeah, let's just make sure that we're all on the same page. So let's say use a stack. So I'm going to push starting from, say, the beginning, right? So I'm going to push them all into a stack. So let's say I have a stack here, and I'm going to call push of my 0th element, right? So I'm going to push my 0th element onto the stack. Then I'm going to push my first one, which happens to also be a 1. Now I'll push the one in slot 2, which is a -2. Push the one at slot 4, or at slot 3, which is a 4. Push the one at slot 4, which is a 5. So now I've got this nice stack here. And so first off, can someone else tell me what can I do with this stack now to get my final reversed array? Yeah.
You can just pop it back like starting at 0.
Yeah, so now I can just pop, if I just call pop 5 times, and say when I pop my first pop, I should put it in slot 0. My second pop, I should put it in slot 1. Third pop, slot 2, etc. Cool. So yeah, that would do that. That would do it, and yeah.
It's only 2n, right? Not n squared.
Yeah. So why would you say that?
Well, just because like you go over n elements at the start when you push them all, and then you just reverse it when you pop them. So it's just n.
Yeah. So this is our first time through. It's big O of n, and our second time through, it's also big O of n. Nice. I think that was one of the bonus questions for the day too. So you already did it. Wow. Awesome. So let's try to implement this in Java. Yeah.
I'm just a little confused on the O of n. I get like if we were just pushing them all with the O of n, or like just popping them all with O of n. But like to implement it, you have to do all the pushes first and then all the pops. So in my brain that would require like 2 for loops. And that would still just be O of n, or
It's because the 4 loops aren't inside of each other.
oh, okay.
Yep, exactly, and we'll do it too. So we'll get some more time to think about this. Okay, so I have a day 29 package here. So I'm going to make a class, if I can even remember how to do that, because it's been so long. Okay, I'm going to call this stack algs, because that is what it is called on the lecture site. So, okay, stack algs, let's make this big, nice and big. So I'm gonna have a main here, and I'll just, let's see, what did we call it? Called it reverse. So in the end, we're going to want to be able to reverse an array. So I'm just gonna make one for us. This is the one from, well, it's not quite from the book, but let's say we have this array. We're using the wrapper type integer, and so we're going to want to be able to call reverse of A, and then A should be reversed. But let's implement that so that we can actually call it. So I'm going to make a static method, reverse, and we'll just make it generic because the book does. So this is going to be able to take in, I guess when you're making a static method, and this is how you say that the method is generic. So the type parameter is E here. Oops. Parameter E. So this is where we get to specify a type. Let's see. So we're going to take in an array of type E. And now, what will we do with it? Okay, so let's think back to our solution. So we need a stack. Great. So we've got our array A, and we also need a stack. And if we don't want to implement it ourselves, which is totally fine, we can just import java.util.stack. And now we have the data type stack to work with. We know that it has, we looked at the website, we saw it has push and pop, so we're good to go there. So let's make one of these. And Java stack is also generic, just like the ones that we've implemented. So we want the stack to hold data type E. I'm going to call it, the book calls it buffer, just kind of like some temporary memory kind of that we've reserved. But that's just the name of the variable. And so we're making a new stack, type E. And with the Java stack, I guess I'm assuming that it can be dynamically changed size, or maybe it's a linked list. Regardless, we don't need to put a capacity in there. So for your stacks that you make with array, that you implement using arrays, I think maybe you have a constructor that, or maybe you have a default capacity. I can't remember. But this constructor is empty. Okay, so we've got this empty stack. It's called buffer. We've got this array A. So how can we already said it. We need to push everybody on and then pop everybody off. So any ideas on how I can push everything onto the stack? Yeah.
For each loop.
Yeah, okay, so let's see. So
No, maybe not for each,
I
because
think
that'll get the values of it. No.
I think you can do a for each loop. The book doesn't do a for each loop, but we can definitely try it. I think it should work.
Yeah.
So for what? For E element in array, we're going to call buffer.push of element. All right, we're not getting any complaints from the compiler at least, so that's good. Great, okay, and now someone else want to tell me what should I do next? So and to be clear, I want to overwrite A. I don't want to make a new array or anything like that. Sorry. Yeah.
You could just have like another for loop that like starts at like I equals 0 and goes through.
Yeah.
And just A like index I is just buffer not off.
Yeah. Oh, yeah, okay. So we're starting at 0, going up to the length of A, incrementing by 1, and we're just going to replace A at slot I with buffer.pop. Great. Okay, well, let's see. Okay, so we got A is, and I think, let's see, arrays.toString is how we print out arrays, except we probably don't have it yet. Oh, because I need a plus. Cool. So it automatically imported java.util.arrays for me, so that's nice. And that's how we're gonna have a nice printing of this of A. And now let's print it out. So we're gonna print it out before and after. Oh, looks like I already have some examples there, but yeah, so great. We successfully reversed our list, and we could do this with a different type. Say we had, I'll just steal the one from the website so you can see the finalized. Oh, no, it's not. Actually, no, then I'm going to show you what our second algorithm. So I'll just look at my notes. So say we have an array of strings, and it's cat, dog, mouse. Well, we can also call reverse. Since reverse was generic, we can also call reverse on S. And we will also successfully reverse our array. S is this. And we can see it afterwards as well. Cat, dog, mouse. Great. Cat, dog, mouse. Awesome. So we just wrote our first algorithm using a stack. So any questions, comments? Now, hopefully, if you were asked, and yeah, this is a great exercise. If you were asked what is the runtime of this method, well, you would say, okay, there is a for loop where we walk over the array, and then independently another for loop where we basically walk over the array again. So we do a big O of n thing twice, so it's still big O of n is what we would say. Cool. Okay, so let's hop over to queues, not decks yet, because I want to show how we can implement a queue using an array. So for Project 4, you don't have to implement a queue using an array, but I did want to talk about it in class because it uses this kind of cool idea, which is that we can, if we fix an array of size n, we can use it in a sort of circular fashion. So what you'd want to imagine is that we have basically this part of the array is representing our queue at this point, but when we think about adding something, so let's say I want to enqueue something else, then I would want to put in, I'd want to fill in this square, right? How's that looking? Kind of yellow. Great. I'd want to fill in that square. So, okay, we can do that. Maybe I call enqueue again, fill in another square. But when I call dequeue, right, what needs to happen? Well, I have to remove the thing here, right? And so that's how we end up getting this sort of circular use of our array. And so eventually, you can see in this second one here, once we've added enough, if we keep adding here, here, after we add here, we're going to have to add at the beginning, right? We want to use our array to its full capacity, even though we're kind of wrapping around. And so this one shows how at some point we might be actually wrapped around using both the end and the start of the array, but we still kind of think of it as one queue, or it's still acting as our one queue. So could anybody tell me if I call, let's say we're in the second case, and I call dequeue, which position, it's labeled, which position am I going to take an element from and return it? Yeah, it's still F, right? So F, in our normal configuration where we're not wrapped around, it's clearly that's the front, but still F is representing the front. Similarly, if I were to call NQ, I'm going to have to put it here, which is the end, even though it's actually an earlier index. So, how do we do this? Well, we're going to have two fields, two instance variables, that keep track of both the front, so that's F, and the number of elements that we've stored. So we could always get the length as maybe we're keeping track of it as n. Let's see what we end up doing. We can certainly get it as data.length if our array is called data, then this n would be data.length, right? So we keep track of where the front is, and then also how many elements are in our queue. And then if we need to get, so we know where the front is. We're storing F all the time. But if we need to get the front, we have to do something clever. And what that is we're going to have to use mod. So does everybody remember what mod does? It's kind of this like circular arithmetic. Yeah, it has to do with remainders. Well, yeah, it is the remainder, I guess. Yeah, it's precisely the remainder. So, yeah, if I mod by a number, so I guess it only makes sense for integers. If I take mod by some integer, then it's like I divide by that integer, and then what I get back is the remainder. So for example, like I'm thinking 14 mod 10. Anybody know what that is? Sure. 4, yeah. I think maybe when you learn this, sometimes you call it clock arithmetic because it's kind of like what you would do for a clock, right? Like if it's 33 minutes after the hour and you add 30, it's not 63, it's 3, which is 63 mod 60. Anybody remember in other programming languages that you've seen what the mod operator is? Yeah. So we have two slashes. Maybe it is. I don't know. I actually haven't seen that one. Yeah.
It should just be a %, right?
Yeah. So at least in Java and most languages that I use regularly, it is the % sign is the mod operator. So if we look at this, what does it look like to implement this? I actually, in my project, I have it open. Okay, so in my project 4, so you don't need an array queue in project 4 unless you want to make one. But in my project 4, since we have the queue interface, so let's pull that up again. So here's the queue interface from project 4. So in my project 4 package, I have a new file that's called array queue, also generic, implements queue. So that means that I have to have the method size is empty and queue first and dequeue. But here's how we actually implement our array queue. So one choice that we've made is we've made a default capacity of 10. And so we're using the final keyword to say that this is it's a constant. It's never going to change. And so we have our no argument constructor, just kind of a remembering Java, because it's been a while since we've really written a lot of Java, our no argument constructor is using the this keyword to call the constructor that has an argument, right? So how do we initialize our array queue? Well, we create an array of type E with whatever capacity we say. And one thing, I already got a question on this for project 4, is that you'll notice that your IDE through your compiler is giving you a warning about this cast. So here we're saying cast this array of type object to an array of type E, and it's saying, hey, that's not necessarily a safe thing to do, warning, but we can just ignore that. So you will also get this warning in your project 4 when you make your array stack. You don't have to make an array queue, but you do have to make an array stack. Okay, so let's look at some easy ones. So size, just return size, right? Size is keeping track of how many elements are in our queue. Is empty, just return whether size is 0. Okay, so now let's look at some more interesting ones. So we've got enqueue here, and I don't know if we actually talked about this, but does anybody know sort of what are we doing, or have any guesses about what are we doing when we have this throws illegal state exception before the method definition? I don't think that we actually talked about this when we talked about exceptions. Any idea what this is doing?
We're not throwing an error intentionally. No, we are.
No, I was just kind of nodding
Cool, yeah.
continue. Yeah, I don't know. But
Because, we have the brackets afterwards.
Yeah, so it's not like
it's
it's not something that's executed. It's just kind of telling whoever uses this this enqueue method that there is a possibility that it will throw this exception. So you might want to handle that in your code, basically. So this is kind of an optional thing that we can do if we are going to throw an exception in a method. If we're writing a public method and it does throw an exception, then we can put this throws that type of exception. Basically it's kind of a warning. So it's optional, but can be helpful to yourself down the line or other people that are using your code. Okay, so what is this? So when do we throw this illegal state exception? Just looking at what's written here. What would be in words? Yeah, what would be going on?
Maybe try and add more elements when it's already full.
Yeah, there's too many in there. So looking back at our picture over here, we may have been in this state, in this bottom state here, and we added to the rear, we added, etc. And now we've added a whole lot. We've added till it's full, and so that would mean that our size field is equal to data.length. Size equals data.length, and hey, you can't add any more once size equals data.length. In this case, we'll talk about dynamic arrays on Monday and how we can actually make bigger arrays if we want to. But for now, that's how we think of arrays, is they have a fixed size. So now here's kind of the crux of this, right? This is where we figure out where to add. Okay, so we've already checked that there's space. So now, if we look back at this, sort of our description here, can Can anybody tell me what variable name over here, what does this avail variable sort of map onto back on that other slide we were just looking at? Or even not the variable name, like what is avail representing? Yeah.
The next available place in the MQ based on where it says it starts the MQ, and then the elements after that. And it uses the mod just so that if it exceeds the length of the array.
Yeah, exactly. So this tells us where we can actually put our element. So in the easy case, it would just, we start at where's the front of our queue, basically. It's at F, and we add size, and this is where it would be. Okay, I do have oh yeah, no, you do see my cursor. Might be small, but you do see it. Okay, we start at F, we add, like this is where F plus size would be, right? And that's where we want to add. In the more difficult case, and this is when we need and so when we mod, like if we mod, just as a little mod review, if I had something like, let's say, 4 plus 10 mod 15, can anybody tell me what's the result of that going to be? Or maybe I'll make this even bigger because this is mod 20. What's 4 plus 10 mod 20? Yeah. Okay, so 4 plus 10. So I put the 4 plus 10 in parentheses. So we do 4 plus 10 is 14. 14 mod 20. So mod is going to give me back my remainder if I divide by that. And so this is a little bit confusing, right? Because I can't put any 20s into 14. So my, I forget what the other thing is. Like, in the end I get, so the remainder, it's true that it goes in 0 times, but the remainder would be 14, right? Because it's like 14 times 0 plus, or 20 times 0 plus 14 is what I would get here, right? And there is a word for this, for that 0, but I'm forgetting it right now. But 14 is the remainder, and that's what we get from the mod. So 14 plus 10 mod 20 would be 14. So the point being, when we don't wrap around, the mod doesn't actually help us at all. But when we do wrap around, then we do need that mod, right? Because that's the only way that I could get the correct R here. So let's say instead we had 14 plus 10 mod 20. Well, 14 plus 10 is 24, and then when I mod by 20, then I get 4, and that's how I would get this R. Kind of just guessing with those numbers, but that's how I get this R. So that is a sort of circular queue idea that we can use to implement a circular array that we can use to implement a queue. The last thing I wanted to cover today is, and intro a sort of write another algorithm, is a deck or a double-ended queue. Yeah. Anybody? have any ideas what a deck is? What operations it supports? I guess you had an idea.
At first, at last, and then pop. I mean, it really smells to me like a doubly linked list, like an array-based doubly linked list. How far off am I though? I don't know.
Well, think on more on the level of our stacks and our queues. Like our stacks and our queues, we, as programmers, we care how they're implemented, but when we talk about them as stacks and queues, we don't actually care how they're implemented. We just care what methods they have and what data they store. So what if, basically, the point of a double-ended queue is to be both a stack and a queue at the same time. So our stacks, we push and we pop the top. Our queues, we were able to add to the top and remove from the bottom. This is our data. So a double-ended queue or deck, it's going to allow us to add to the front and also remove from the front, and also add to the back and remove from the back. So basically, instead of limiting ourselves to only sort of 2 out of these 4 possible operations, we have all 4 available. And let's double check on the lecture page what they are. So a deck has add first and remove first. I think I missed something here, but basically we should have add first, add last, remove first, and remove last. And yeah, we call this a deck. Easy to get it confused with DQ, but don't get it confused with DQ. It's a deck. And here are its sort of most important methods. Okay, let's end with one more fun thing, which is another application of stacks. And I do want to talk about this because this is basically the same, it's a slightly easier version of the same problem that you have on Project 4. So let's say that my problem is I want to check whether a sequence of parentheses is correct or incorrect, right? So it's correct if my parentheses match. Basically, I don't leave anybody hanging. I don't try to close a pair when I don't have one available. So like this one is correct because, okay, this one's match is over here. This one matches here. This one matches here. This one matches here. But over here, there's nobody to match with this, but this one over here, we can kind of think of it as nobody to match with that one. But checking these, like I was definitely using my human brain, right? I was like matching them up. And it turns out that there's actually a big O of n time algorithm to do this check. And it uses a stack. So does anybody have any ideas about how we might use a stack to do this? Sure, I saw your hand, I think.
Whenever that left set of parentheses are uncharacteristic to right, you push 1 into every right set of parentheses and pop.
Yeah.
As long as you get back to 0 in the code, try to pop and you have that one add, and after that it's multiple numbers.
Yeah, so basically, maintain a stack, and for every opening paren, for every open we're going to push onto it. We could really push anything onto it because we're just going to check whether there's something there. But why not? We'll just push an open paren onto it. So for example, here we see one, we see another one, push another one on. But then when we get here, well, we don't really care how many are in our stack. We don't, as long as there is one to match with, right? And so push these guys, and then when we see a closing, check that stack is not my ends always look like H's. Apologize. Okay. Not empty, right? So that means there was something to match with. So we pop that off. Now we're on here, so we're going to push another one on. We're here, we're going to push another one on. We're here, we need a pop. Okay, let's pop it off. We're here, need a pop. Great, pop it off. We're here, need to pop. And then at the end, we need to make sure that our stack is empty. So what would it mean if at the end of that process, we still had one on here? Anyone have any thoughts? What would that mean? Or which example input would have that problem? So I'm seeing number 2 would have that. Oh, is my label? Sorry. Yeah, so, okay, if we say this is 1, 2, 3. So here we have too many opening parentheses, right? So we open here, we close it, but then we open 2 and we only close 1. So number 2 would have this problem. Cool, so we can write this in Java. I won't make us do it today, but it is in stackalgs.java. And basically, you are going to do something just a little bit more complicated than this for your first sort of algorithmic problem in Project 4. So hopefully this can be a helpful example for that. And have a good weekend.
You too.
Thank you.